Well, just as a start of the remaining part, let's begin with the conclusion, just to sum up what we have just heard. This is very important, this is mandatory for keeping the system free from biases, mainly the rainbow bias. And the only way to perform a bias-free system calibration is to use a flat target or a single target. Keep it in mind, the reflex has to be sharp. Only from a flat target or a single prism at exactly known distances. We will just deal with the exactly known distances to which the laser light has to travel. I just heard from a colleague that it is not always straightforward to perform a very short calibration run because of some specifics on the ranging electronics. The ranging targets at short distance are preferable. They are easier to control, they are accessible, lower effect of environmental influence on the data. Okay, I have forgotten to say, of course you cannot go below a certain amount, a certain time interval. Both the Stanford Research System Counter as the Riga event timer, they are limited by a minimum time interval which can be measured. This is due to the processing strategy which is used into the ranging electronics. This has to be taken into account. But in case you know that very well, there is a simple technique. Use a short wave target and prolongate the electronic wave. For instance, by introducing whether an optical fiber, as all the Pinodas and Calvis do here in their system, Riga, or to introduce a high quality and temperature stabilized coaxial camera. But you have to apply it for both the ranging and target calibration. The system has to be equal in both sides, because you are removing the influence of the system delay both in the ground calibration run and in the system, and it is performing satellite measurements. Then a suggestion, if possible, perform statistics of the target calibration run, because you see the long time behavior of the ranging system, and I can assure you, even if you have long since forgotten the year, let's say 2012, there will be sooner or later a question from one or two processing centers. What happened at your station in May 2006? We are just reprocessing all the latest passes from your station and found a strange behavior on those and those and those days. What happened in those days? And in case you can look at some overview what happened to your system delay, you'll likely get an idea. It does not free you from keeping a station log that maybe the observer was not in best shape, or the telescope axis was a little bit out of alignment, or there was a heavy fog or something like that. But the long time behavior of the target calibration is a very, very nice tool, and you see slow effects like the aging of components clearly visible. And this was the last slide I showed before the short break. The system delay is usually not fixed over time. It depends on parameters like detector performance and especially temperature. I see it clearly when I start to operate a system in the evening. I'm usually not performing ranging at night. My specialty is the daylight tracking, so I start in the early morning. Let's say in the case I'm getting there to the ranging station at 5 in the morning, open the roof. Now in autumn we have maybe 5 degrees centigrade around. Start ranging, perform target calibration, and then when the sun rises and around midday, I have a different calibration because the temperature has risen, not because parameters like the laser and detector performance have changed over that time. They are more or less stabilized. The laser is in the temperature stabilized room, and the detector as well. But especially the cables are outside, and they are subject to variations of traveling time with temperature. And for this reason, I always propose and tell our observers to perform calibration runs as often as reasonable. Some of them, they do not listen to me, they switch on the system, perform a calibration. The second one after 3 hours, because the ranging software reminds them to do that. The third one, just before leaving the station, so I have 3 calibration runs over the night and have to perform linear trends between them, which can work, but which will not work so well in case the temperature changes. So do it as often as possible. The amount of work is not so high. Now, as I told you, as the last thing I would like to consider is the role of the invariant point and how to perform a dedicated survey of that. Again, the 1 meter TPL system. The service system reference point is defined as the invariant point, which does not change, its position independent on the pointing of the telescope. That means, in case we would say, oh, this is our telescope reference point, then I would say, okay, then in case you turn the telescope by 180 degrees, it is this display. There is only one point which is invariant. This is the intersection of the azimuth and the elevation axis. The 2-axis telescopes has an azimuth axis and an elevation axis. They have one intersection point, and regardless how you point your telescope, this virtual point remains in position. This is different for a bistatic system, as we have in Potsdam. There, the system reference point is halfway between the system reference points of the individual telescopes. That means the receiving telescope has a system reference point, which is the intersection of the azimuth and the elevation axis. The transmit telescope has an invariant point, which is the intersection between the azimuth and the elevation axis. And exactly halfway in between that is the invariant point of the whole system. And you have to find out where this is, and you have to supervise it from time to time by means of a local geodetic survey, because in case you especially operate more than one cosmic geodetic method on your station, you have to tie your invariant point to the local network. One example. In Potsdam, we have started to perform laser ranging in the early 1970s. As I told you, we had a photographic tracking camera which was attached with a laser and which was used for about nearly 20 years over time. Then we found out that the system was not capable of further upgrading to 3rd generation. In 1990, we got the opportunity to take an empty building which was formerly housing a photographical Zenith telescope. Photographical Zenith telescope has the charm that its main mirror consists of liquid mercury. It means it is a floating mirror which is aligning itself by no technical means parallel to the gradient of the gravity. So this is a very nice thing. But on the other hand, mercury is giving rise to evaporation, and this mercury vapor is extremely toxic. So there was plenty of exhaust ventilators to bring those fumes outside. But after a few years, this building was declared clean, and we were allowed to install the TPL there. The problem is, now we are starting, after the old system was calibrated very well and its position was very well known, with an entirely new system which has to be inserted and tied to the local geodetic network. And the same happened in 2002 when we started again. We stopped operation with this 1 meter TPL in 2004 for 2 reasons. The first one was that the system was a little bit out of shape. It was a self-made laser. We got no more spare parts for it. And you see also, which is quite unusual for a satellite laser ranging station, we had very nice high trees close by. It was no problem for the satellite telescope. It was even welcome because those trees are capturing the wind and making the atmosphere a little bit more calm. But in the west, here's east, there's south, there's north. You could see the satellites only above the tips of the trees. We were not allowed to cut them down. Environmental protection, especially in our area. In winter times was no problem. The leaves were not there, so we could fire through the trees. It was looking nice. The scattered light was attracting some attention, but okay. In 2004, we got the opportunity to install an entire new system on a pillar in the new premises of the GFZ. You will see an overview of the map, but again, this was away from the old system, and now we had just managed to get precise coordinates, tie it to the local reference system, and now we had the task to transform that to the new system to find about the appropriate coordinates and to tie those. Here is from Google Earth an overview of the area where I'm working. This is the famous L.Grunwaldt area in Potsdam. The only building which is mentioned in the tourist guide is the Einstein Tower, the famous solar observatory set up in 1923 for detection of one of the predicted effects of the general theory of relativity, the gravitational redshift. It was found there only in 1958, but it doesn't matter. The Telegrafenberg area was made as a campus for science, starting in 1874, and it was a small city fully dedicated to sciences, started with astrophysics, meteorology, and solar physics, geodesy in 1895, 1996, and finally also came the polar research. It was used for that all the times. Now, where are our SLR systems? The SLR number 1, the 1181, was on the Helmut Tower. The 1 meter TPL was relatively close by. I showed you this example of direct ranging between those two buildings for 40 meters. But the new third and fourth generation is here under this dome within the new premises of the Geoforschungszentrum, the GFC buildings. It means you have to find the references between those laser stations and the other systems. The IGS antenna, for instance, the former RARE system, you will see that in the following slides. And you see also that we have a quite complicated geometry. This area is extended mainly north-south. This is exactly the northern direction. It is practically not extended in the east-west. And this is some fact the geodesists do not like very much. Here we have more detailed description, and I have shown you here where we are. The Helmut Tower was carrying the first system, the 1181. It is not mentioned here because at the time the latest survey was performed, the roof could not be opened anymore. When the telescope was transported away, the energy was switched off, everything started to rust, there was no dehumidifying, and this historical building is now lost for science because we cannot open the roof anymore. The SLR 8036 is a 1 meter TPL here, the reference station for the IGS, the GPS station here, the former RARE station on the water tower of the former astrophysical observatory, and the new SLR here. So we decided to set up a network, 2 networks, one supported by GPS, and you see the single points. This is the reference point of the POTS, this is the IGS station. This is a couple of points in the vicinity of the new laser, and here are some intermediate points. And this is the usual network geometry, and the student of geodesy who was hired to perform this task within his diploma thesis work said, oh no, that's not feasible, that will give a very, very bad resolution, and he insisted on installing a temporary point which extended the network a little bit to the side. But nevertheless, you see the scales in meters. The extension north-south is about 700 or 600 meters. The extension east-west only 200, 250 meters. So this is not the best geometry, but we could not cut down trees in order to install here that point there. And there was a second network for terrestrial survey. It is not possible, and this is something one has to explain to today's students in geodesy again and again. simply put a GPS antenna there, record for 2 days, put it to another point, write down, and you're ready. In case you want to access, for instance, the invariant points of an SLR station, you have to be skilled in the classical geodetic methods as well, in leveling, in tachymetry, even in applying rulers. And you see, some of those points are contained in both networks, but not all of them. There was the delicate question how to find out the invariant point of such a large system like the TPL mount from Riga with external needs. This is a huge telescope, and there was some clever idea of the student. He said, we define some markers in the wall crest of this building, 1, 2, 3, 4, and point tachymeter over that. Tachymeter and simple angular measurement, and we place a small reference prism outside somewhere on the tube so that it is visible from those 4 points. And now we start to rotate the system, at first in azimuth, by 360 degrees in steps, and we perform measurements from all 4 reference points to this reference point. Then we start to move the elevation axis from 0 to 90 degrees and perform measurements again. In principle, in reality, it was performed. We let the elevation at 0, rotated it, performed elevation at 10 degrees, rotated it, and so on and so on. So the slope distances were recorded, and they defined part of the sphere. In case you rotate the telescope systematically around both axes and measure the distance to a reference point, you will get points of a sphere, which can be finally adjusted, and the center of the sphere, which is found by mathematical adjustment, is the invariant point, with reference to those external markers, and those external markers can be accessed by other geodetic survey methods as well. The starting point of this geodetic survey was the reference antenna POTS. This is our IGS antenna. It is located on a pillar of the former Geodetic Institute in Potsdam. It is so important that we supervise it day and night by a video camera. This is the invariant reference point, which is used there. I've made there a cross. This is not there in reality, this cross, but this is very well defined. The reference point 8500 you have seen in this network. Very important, it is contained in both of the networks. It's located on top of the water tower, former times, when the local area was founded there in 1874. The first idea the old Prussian scientists had to have a local water supply. So they had their own well and their own high tank to supply sufficient pressure, and for that was made this water tower in the main astrophysical observatory. And in later times there was made the Prare station. Prare was a precise range and range rate equipment, this is this abbreviation, invented by a German enterprise together with the Technical University of Munich to perform two-way ranges in the microwave region between the ground station and the satellite. The satellite antenna had to be moved to follow the satellite. Like a laser ranging telescope, it was the weak point. The good point was that it was a true two-way ranging system. The uplink was in the S-band and the downlink was in the X-band. So we had a dual wavelength system to overcome atmospheric effects acting on radio stations and radio waves. Now we are here in the location of the new laser, and you see in the background an intermediate point 8700. Again, this point was shared both by the GPS and by the local terrestrial survey network, and was located on top of the former Meteorological Institute. It could not be there for a permanent time, but for the time of the survey for a few weeks, it was located there. Here in the foreground, you see the aperture of the receiving telescope, 40 centimeter in diameter. And finally, we have the two located and defined markers here in the central pillar of the new station buildings, 8800 and 8900, and they were referenced to the reference point halfway between the two telescopes by a geodetic survey as well. The problem for a normal telescope is that you can never put a GPS antenna into the invariant point, because the invariant point, the intersection between the azimuth and the elevation axis, is deep within the telescope. There you cannot place a GPS antenna. The good thing in our system is that there is simply air in between. There our reference point is. So our reference point is not manifested by any mechanical point, but it is accessible with geodetic means, and you can directly place a GPS antenna on it. It's a good thing. And our dome, fortunately, is transmissible for radio waves. So we had reference markers within the pillar and measured carefully by conventional rulers and by leveling the distance between all of them. So the conclusion that the system reference point of an SLR system has to be tied to external markers within a local geodetic network by means of a survey from time to time. The question is, what means from time to time? How often would you have to do that? My proposal is at least once within 5 to 10 years. The coordinates of those local markers within the local system usually are well defined. They are put into some stone monuments and they will not run away. The reference point to be tied to the local network is then especially important when you operate other space geodetic methods, at least GNSS or VLBI, in your very area. You are asked in a questionnaire by the International Laser Ranging Service which other cosmic geodetic systems are collocated with your SLR system. And you have to use a classical geodesic method in combination with GPS. This is favorable because those two systems have fully different working principles, and in case the derived coordinates and the coordinates you get from them after leveling, after tachymetry, after GPS adjustment of the network are adjusted to, let's say, better than 1 millimeter, then you can be sure that you have done a good job. And within the local geodetic network at Potsdam Telegrafenberg, we found a formal error in the order of 1 millimeter or less for the ITRF coordinates. This is important last step, which I have omitted here. You have to bring your local coordinates in the coordinates of the International Terrestrial Reference Frame, but this is just a coordinate transformation which is defined and which can be performed by a student without any big problems of the survey points. And I have to give credit that the survey was performed by Markus Böller. I was fascinated how he did it. He had a lot of ideas how to do this with his diploma thesis. I'm not a geodesist, I had no idea. I told him, okay, yeah, we have to do this, and this is a very quite nice task for you. And to learn something, I was going with him over the Telegrafenberg area as his assistant, putting the levels and holding the prisms or performing some tachymetric measurements. It was quite a new experience for me. And I propose you do it in case you can do it as well and you are not geologist. You will learn a lot, and you will be fascinated with about the ultimate accuracy you can reach. Okay, this concludes my presentation. A few words about the system calibration, the importance of the reference points. I hope I have stressed what I wanted to say in sufficient detail. My message is keep attention to the system calibration, keep attention to obtaining the proper system delay, then your system will be very well recognized by the international community. Many thanks for your attention.